Hello and welcome to another continuation of a previous episode of How to Understand X. Today we're going to be continuing our talk about integrals, and we're just going to get right into it because we do have quite a bit to talk about. We're going to talk about like some properties of integrals. They do carry over somewhat from derivatives, and we are going to do some U sub, maybe even talk about multivariable calculus a little bit, touch on some multiple integrals. So let's get into it. Uh, Integrals have properties like derivatives. There's the sum rule, the product rule, the sum and difference rule. The product rule, the quotient rule, chain rule. There's a bunch of them, right? And like the constant rule. So most of these are relatively intuitive for both indefinite and definite integrals. So I'm just gonna, show some pretty useful ones. Like for example, let's do k f of x dx. And at this point, we've established that definite integrals show area under the curve, while indefinite integrals, integration is both area under the curve and anti-differentiation. So if we do not have a definite integral and we have an indefinite integral, there is no bounds to this integral, so it's indefinite. This will just be a simple antiderivative. That is going to be k f of x dx. So what's this saying? We can simply factor out constants when we have integrals to do. And for this, we're just going to say, based on the fundamental theorem of calculus, if big F prime x is equal to f of x, and k f prime x is equal to k f of x, then that means that the antiderivative of k f of x, since we said that k f prime x is supposed to be the same as k lowercase f of x, that means that k f of x dx, this antiderivative, not plus c just yet, is going to be k f of x plus c, which we said was k f of x dx, because again, big F of x is equal to the integral of f of x dx, lowercase f of x dx. And this c is an important thing for you to add to any indefinite integral. The derivative of a constant, as we've said many times, is going to be 0. If you draw a straight line, can be any y value, let's say y equals 2 for now. This is a straight line with a slope of 0, so the function itself is a constant, and you pick any point, and you draw a tangent line to that point. That slope of the tangent line is going to be 0, so the derivative of a constant is going to be 0. And if the derivative of a constant is 0, we have to assume that, let's not use the actual thing right now. Let's say f of x dx is the same as f of x plus 0 dx. So we have to actually integrate 0 as well. And 0, again, if c prime is equal to 0, then if we were to, integrate 0 dx, we should just get c. Even though it's not like, accurate notation or anything, it's just if the derivative of a constant is 0, we have to acknowledge that there could be a constant added to any function. And the idea of splitting integrals is something that we also need to talk about. And that is going to be somewhat similar to the sum and difference rules of derivatives, but this time we're going to just do sum and difference of integrals. This proof is also going to be relatively simple. We have the indefinite integral of the sum of two functions, f of x plus, let's use plus or minus. We're going to try and prove both of these at the same time. f of x plus or minus g of x dx is equal to the integral of f of x dx plus or minus the integral of g of x dx. This is relatively similar to the sum rule of derivatives. You can split two separate functions if, well, a derivative is a sum of two functions, and it seems relatively intuitive, but let's use our actual knowledge. We said that f of x is supposed to be the integral of f of x dx, right? So f prime x is supposed to equal f of x, and from here we can say that big F of x and big G of x, which we are going to describe as the original function before, like lowercase g of x. So f big F of x plus or minus g of x, big G. This derivative is equal to f prime x plus or minus g prime x, and that means that the integral of f of x plus or minus g of x dx is going to be equal to f of x plus or minus g of x plus c, which is, again, just a different way of writing our first step. And this is because f of x plus g of x, or big F and big G, are going to be the antiderivatives of lowercase f and lowercase g, regardless of whatever sign we have in there. So, it's not like a super formal proof or anything, but I hope you can see that connection between the sum and difference rules of derivatives and how that connects to integrals as well, because again, differentiation is an operation. So the inverse of differentiation, which is integration, is also an operation. So it usually follows the same rules as its inverse operation. Now let's do another somewhat, well, not somewhat, we're going to go from, I'm actually going to skip product rule. We will talk about that in the form of U sub, not U sub, integration by parts. U sub is more like how you would solve for chain rule. So we will get to U sub and integration by parts in a little bit, but right now let's talk about some proofs of definite integrals. So yeah, those two ideas that you can factor out constants and you can split indefinite integrals. Those are probably the most important ideas for indefinite integrals as of right now. But when we talk about indefinite integrals, there are a lot of important rules that we need to know. First off, the definite integral from a to b of f of x dx is equal to negative integral from b to a of f of x dx. This proof is going to have to use our formal definition of the integral, or the definite integral. So let's write that out. We said that the integral from from a to b is going to be of f of x dx is going to be equal to the limit as n approaches infinity of this series, incrementing at 1, of f of xi times change in x, where change in x is equal to b minus a over n. And again, this is just saying that if this is a y value and this is an x value, then you're going to have area equals xy, which is again going to be base times height. So we have a very, very thin rectangle. Again, if n is infinity, then b minus a over n, I don't know why that keeps happening, b minus a over n is going to be a very, very small number. So delta x is going to be a small number. So you're going to have a bunch of very thin rectangles, and when you add them all up, that's the area under the curve. That's what the definition of the definite integral is saying. And then we also have the integral from, oh my god, from b to a of f of x dx is equal to the limit as n approaches infinity of the same series of fxi times change in x, where this time change in x is equal to a minus b over n. And a minus b over n can also be written as negative b minus a over n, right? But we're getting a little bit ahead of ourselves. We can also write, perhaps more accurately, we can say that b minus a over n can be written as negative a minus b over n, right? If we just bring that negative over there, we'd have negative a plus b, and a negative become positive. So we can pull out that negative, so we have negative a minus b over n. And now let's put this back into our definition. I'm just going to erase this down here. Now, we are saying, well, we are trying to prove that the integral from a to b is the negative of the integral from b to a. So when we plug in b minus a over n for this delta x, and then we change that to negative a minus b over n, we're kind of done, essentially. So by limit properties, we know that we can factor out this negative all the way out there. Well, technically, we're going to factor it out of the sum, and then once we factor out of the sum, by limit properties, we know that we can factor out negative 1, and so we should get the negative limit as n approaches infinity of this same infinite series. F is in the wrong spot. It's okay. I'll just kind of put parentheses around this. Fxi times delta x, which in this case is a minus b over n, now that we've factored out that negative. And when we said that delta x is equal to a minus b over n, we said that the bounds actually changed to from b to a. So now we just plug back in our original idea. So now we simply get this is the negative integral from b to a of f of x dx. And this is pretty useful for when you're solving integrals when given a graph. It's just you see how to work with kind of impossible domains. Like imagine if a was equal to 5 and then b was equal to 3. When you do this integral from 5 to 3, it's hard to kind of imagine how this would look on a graph. If this is some f of x, your a is after your b, so it's not really possible to see some a to b area real easily. You just have to flip your a and b and get a negative integral. So yeah, that's how you can manipulate your definite integrals to be more solvable. And now let's talk about another one. Let's do the integral from a to a of f of x dx is equal to 0. This one's a nice and easy one. We're just going to go back to our formal definition of the integral. We say that if we're doing an integral from a to a of f of x dx, that's going to be equal to limit and approaching infinity series and I equals 1 fxi times delta x, which in this case is going to be b minus a, so a minus a, over n, so delta x in this case is going to be 0, and now anything times 0 is going to be 0, so all of that's going to be 0. And when you add a bunch of zeros together, you're going to get 0, and regardless of what n is, this is still going to all evaluate to 0. So, yeah, relatively simple. And, yeah, I mean, I think that's probably the most important thing that we need to know. And, let's see. We do need to talk about how to solve for this definite integral. And that's that should be something that I mentioned earlier. But essentially, let's go back to our drawings. We said that integration is supposed to be the antiderivative, right? And imagine f of x is some curve, a to b is right here. And we describe all of this as the integral from b to 0, right? Well, actually, let's not go into some unnecessarily complicated stuff. Let's keep it nice and simple. Let's just draw from a to b. X, y, we have a over here and b over here. F of x is some curve. We originally defined the definite integral as area under the curve on some, on some, like, thing that's happening, right? And the reason that we can solve for definite integrals is somewhat interesting. So let's write down. We have the integral from a to b of f of x dx. And we said that f prime x is equal to f of x, right? F of x is supposed to be the the antiderivative of f prime x. But now we need to see how to get this. That means that we're going to have to do big F of b minus big F of a. Now, what does this mean? Let's talk about the definition of the derivative first. Derivative is change over some interval, right? We are seeing the slope of a tangent line, something that is continuously changing, and we have to see just the amount of change that happens on any given interval. If we are undoing the derivative by, common sense, we should be able to know that when we undo the derivative, we're simply seeing the amount of change that's happened, right? In case I'm not making myself clear, it's like we have a derivative. F of x is the derivative of some function, right? And f of x only shows us part of the picture. It shows us the instantaneous rate of change at any given x value. But when we anti-differentiate, we're getting the original function, and when we plug in our values for the original function, we should be getting the area under the curve between 2 points on an interval. And to actually fully illustrate this idea, I'm going to show a quick little proof of it. Now, this one might be a little bit complicated, but it's a lot of notation because this is just an extension of the fundamental theorem of calculus. So let's let g of x be the integral from a to x of f of t dt. And with this expression, f of t dt is just going to evaluate to f of x, once you plug in x, I might be spoiling it just a little bit, but this is a proof, so we know what our final answer is supposed to be. In case I didn't write what the case is that we're trying to prove, which, is definitely important. We're trying to say that the integral from a to b of f of x dx is equal to the antiderivative of lowercase f, big F of b minus big F of a. And now, with this, original idea, when you do the antiderivative, or the definite integral for this one, you're going to have big F of t, where you're trying to evaluate from a to x, and then from here, you plug in f of x minus f of a. Again, we don't know why we're doing this just yet. We're trying to prove why we're doing this, but this is only to show that we know that f prime x is equal to f of x just by, the original part of the fundamental theorem of calculus. We've been talking about how big F is the antiderivative of little f. I mean, little f is the antiderivative of big F. So if this is equal to g of x, when you do g prime x and you differentiate both sides, if we have big F prime x, which is going to be the derivative of big F of x, we're just going to get lowercase f of x, and then derivative of a constant is going to be 0. So, yeah, from here, g of x is equal to that that definite integral, and then when we differentiate both sides with respect to x, we'll get g prime x is equal to lowercase f of x. And, we're all assuming that this interval from a to b for our original proof idea, we're going to say that this interval is continuous, that you can differentiate. We're just going to assume a bunch of stuff, right? And let's also write that g prime x is also equal to f prime x, right? And if we were to, do an indefinite integral of both sides, with respect to x, of course, you're just going to get g of x is equal to uppercase f of x plus c. Again, when you integrate anything, you have to account for a constant that will eventually differentiate to 0. So with those ideas in our head, let's work backwards. That's probably the best way to write this, or to describe what we're going to do. We have big F of b minus big F of a. And now let's plug that into what we said. We said that g of x is equal to f of x plus c, right? Because g prime x is equal to lowercase f of x. So when you do g of x, you'll get big F of x. So from here, we have g of b plus c. We're just plugging b's in for all the x's, and then g of x equals big F of x plus c. So g of b plus c minus g of a plus c, right? And then from here, this will be in parentheses. Minus will distribute to this plus c, so we're going to have c minus c, which is 0, and we're going to be left with g of b minus g of a, right? And then from here, we know that g of x is equal to the integral from a to x of f of t dt. So when we plug in b for x, we'll have the integral from a to b of f of t dt plus the integral from a to a of f of t dt that wasn't written correctly, f of t dt, which again, by one of our earlier proofs, we know that this is supposed to evaluate just to 0. So now we know that big F of b minus big F of a is quite simply, this is starting to get more and more anticlimactic. There we go. Big F of b minus big F of a is equal to the integral from a to b of f of t dt, which is, again, what we're trying to prove, because if we, use different variables, f of x instead of f of t, so f of x dx, if we just say that we are changing our variables to, be function of x, we will have the integral from a to b of f of x dx is equal to big F of b minus big F of a. So, given the definite integral of some function along some, interval, you simply have to do the antiderivative of that function and then plug in those values and then subtract. So, yeah, now we can kind of, work. Well, we actually do have a couple other theorems that are important, but that's probably the most important one for definite integrals, that the integral from a to b of f of x dx is equal to big F of b minus big F of a. Now let's talk about the average function value. This is kind of what we just breezed past in our original definition, or not our definition, our proof for the fundamental theorem of calculus. At the beginning, we have 1 over b minus a is times the integral from a to b of f of x dx. This is going to be the average value of a function. Now, from here, we can kind of just, this is a proof, so we're not going to be able to assume anything, but let's look back at some of our original ideas, right? From our original definition, our formal definition of the definite integral, we said that the definite integral is equal to this limit and approaching infinity of that same series times change in x, where change in x is going to be equal to b minus a over n, where n is again the number of subintervals, which in this case is infinite. Now, xi increments at some random value. We start at I equals 1, but we don't actually know where I is going. It just be any x value possible. But if we were to try and find the average value of fxi, we're just going to have to add everything. We're going to have fx1 plus fx2 plus fx3, and on, all divided by the number of subintervals. If we're trying to find the average y value or f of x value, we're going to have to just add up every f of x value that we have and then divide by the number of values, which in this case is n. And then from here, we can change our order of these. So we can multiply n to both sides, so n delta x is equal to b minus a, and then we'll divide by delta x to get n is equal to b minus a over delta x. And then from here, let's keep that idea in our head. From here, we're just going to do a little bit of manipulation. We have f of the original average value of those functions, because again, we're trying to find the average function value of this definite integral, right? We say that it's just the definite integral divided by b minus a. So from here, we plug our original idea. When we sum up every single f of xi value, we will have fx1 plus fx2 plus fx3, and on, all over n, which we now said was equal to b minus a over delta x. And already, we can bring that delta x to the numerator. When we divide by one of these fractions, we will have delta x up here. So let's rewrite this slightly. Again, you don't really need to write this down. It's not super important to understand why this is the way it is, more just what is being done. So this will be delta x up in the numerator, and then we can rewrite our series. So this is going to be delta x times each of those terms. So let's pull that 1 over b minus a out to the front, and that will be times fx1 delta x plus fx2 delta x plus fx3 delta x, and then on, which again we said was supposed to be, I don't know what happened up there, I equals 1 f of xi times delta x. This is the same thing as an infinite sum where I continues to increment, right? So we can just rewrite this again as all of this as an infinite sum of these f of xi times delta x values, which again is going to be our definition of the integral. So limit as n approaches infinity of this infinite sum f xi dx, or not dx, delta x. So, and then from here, we just substitute back in that integral from a to b. So 1 over b minus a from a to b of f of x dx, which means that we're back at where we started. This is going to be the average value of a function. Again, you don't need to know any of this, but it is nice to kind of see where it comes from. From here, we can do, I think, our last proof of the day. Yeah, probably this is going to be our last proof, even though we are going to do a couple more example problems. So let's do it. We have this following thing. We talked about this before. This is the MVT, or mean value theorem, for integrals. It is as follows. If f is continuous on AB, then there exists a C in AB such that, I'm just using shorthand, it doesn't matter too much the actual notation as long as you see this. The integral from a to b of f of x dx is equal to f of c b minus a. Alright, so let's define, again, big f of x is going to be the antiderivative. So big f of x is going to be the integral from a to x of f of t dt. So let's write that out. F of x is the integral from a to x of f of t dt. And then from here, we know that f prime x is equal to f of x from our fundamental theorem. And then, as we said, f of b minus f of a is going to be the integral from, it's not the integral, it's going to be the evaluation of the definite integral from a to b of f of x dx. And from the mean value theorem of derivatives, if a derivative exists, there must be a c such that a is less than c is less than b. So let's just kind of write this out a little bit. If f of big F of x is continuous, because again, it is differentiable, then there exists a c such that you can find the integral. Not integral, derivative. So f prime c is equal to f of b minus f of a over b minus a, which again is going to be, average rate of change, or another way of writing the derivative. Well, this isn't the instantaneous rate of change, so it's not the derivative, but it is just another expression of continuous change, so it's kind of like in the same niche as a derivative. It's the average rate of change, so f prime c is supposed to be equal to f of b minus f of a over b minus a. So when you solve for f prime c, so f prime c is equal to f of b minus f of a. I don't know why I erased that. F of a over b minus a. When you multiply b minus a to the other side, we have lowercase f of b minus lowercase f of a is equal to f prime c times b minus a, which looks awful similar to our mean value theorem of integrals, and that's because it is rather similar. So let's put that idea on the paper. We know that if we have big f's and we plug that into our original mean value theorem for derivatives, we will also have big f prime c of times b minus a. And then from here, if f prime x is equal to lowercase f of x, then we know that since a of b, f of t dt, is equal to the integral from a to b of f of x dx, that we can actually plug in this f of x for f of t, and we just get f of x, or lowercase f of c, b minus a. Let me write this correctly. Lowercase f of c times b minus a. And again, uppercase f of b minus uppercase f of a is the integral from a to b of f of x dx. So yeah, this is where we started. If f of x is continuous on some interval from a to b, then there is a number where you can just multiply the antiderivative at that number to b minus a, and you get the definite integral. That's just another way of rewriting our mean value theorem that we learned back in our video on derivatives, which I'm remembering I didn't talk about mean value theorem or intermediate value theorem or even extreme value theorem, so I'm probably going to have to do another mini video on that, proving those, talking about those, and just kind of maybe showing some examples of them. But from here, now we can actually do some of the fun stuff. Those are just some of the rules that we ought to know. But now let's do some antiderivatives. And antiderivatives are kind of odd to calculate. I wouldn't say it's all memorization, but you need to know the derivatives for you to know the antiderivatives. When you are given a x to the n, you know that the derivative is going to be n times x to the n minus 1. We talked about how Pascal's triangle proves this, and how there's probably, a way to use this knowing the binomial theorem, which is uses a lot of factorials and n choose k and stuff that I didn't want to talk about, so I just kind of proved it, sort of, with Pascal's triangle, but not actually. We're only going to talk about this in, our language. If we have this is equal to the derivative of x to the power of n, when we are doing the integral, or the indefinite integral for this one, of x to the power of n dx, how are we going to invert this? We want this integral to just be the opposite of this derivative. So I'm not going to quite prove this, I'm simply going to kind of describe it. We have the multiplication of n, so opposite of multiplication is going to be division, 1 over n. And then we have n minus 1. We're going to multiply, we're going to add n plus 1. So let's do a quick indefinite integral. Oh, forgot one last thing. So, wait, let me think. I actually forgot something somewhat important. When we do a derivative, we have to multiply n minus 1 out, right? So for the integral of x to the power of n, we're actually going to have something a little bit interesting. This is actually going to be divided by 1 over n plus 1. I knew that looked a little bit odd. So over n plus 1, and I actually lied. I'm going to show a bit of a proof for this, but we want this n plus 1 to cancel out this n plus 1. If we were to just do the derivative of this, we'd have to multiply this to that to cancel out this fraction, and then subtract 1. So we would just get, x to the power of n, but let's kind of write this out. We know that when we do the integral, we're going to have the antiderivative of some function, right? So our n is going to be incremented by 1. Like if we have x squared, using common sense, we know that the derivative of x cubed will be some multiple of x squared, right? Because derivative of x cubed is 3x squared, which is, again, going to be a multiple of x squared. So every derivative of a function is going to be a multiple of a function that is a degree less than that function. So the derivative of x to the n plus 1 should be some multiple of x to the power of n, right? So let's do the derivative of x to the power of n plus 1. So when we do that, we're going to have n plus 1 out here times x to the n plus 1 minus 1. So this is going to be n plus 1 times x to the power of n. All right? And let's say that let's use ddx notation instead of prime notation, actually. So let's say we have d dx of x to the n plus 1. Again, we're just doing the derivative. Now, I'm going to do something somewhat interesting. I'm going to multiply dx to both sides. I want to have dx on this side so I can actually integrate with respect to x, and then once I have dx to the n plus 1, and I do that indefinite integral, this should just cancel out, right? So we have x to the n plus 1 is equal to, well, n plus 1 is a constant, so we can just pull that out. N plus 1 times the integral of x to the n dx. And now we simply divide by n plus 1 on both sides. So we have the integral of x to n dx is equal to 1 over n plus 1 times x to the n plus 1, or x to the n plus 1 over n plus 1. And this isn't too hard. I mean, I know I made it a lot more complicated than it needed to be, but I'll just show you a couple examples, and I feel like it's pretty intuitive. So this one's going to be the most important one. I would say that the rest are usually tending towards some type of memorization, but let's do it. So we have x squared, the integral of that, and this is going to be 1 over n plus 1 times x to the n plus 1. So n in this case is 2. So 2 there, 2 there. 1 over 2 plus 1 is going to be 3. And then x to the 2 plus 1 is also going to be 3. So, yeah, integral of x squared is going to be 1 cubed x cubed. And that makes sense. If we do this derivative, which again should get us back to x squared because we're doing the antiderivative, so when we do the derivative, two inverse operations will cancel out, so we should just go straight back to x squared. This is n, so we bring that out there. We have 3 times 1/3, x to the 3 minus 1. This cancels out. 3 minus 1 is 2, so we are simply left with x squared, which is where we started. So, yeah, that's relatively normal. And, yeah, let's do a somewhat more weird-looking one. Let's say 7 over 16 x to the power of 8. This might look, difficult, but this is relatively normal as well. 7 over 16 is a constant, so we can pull that out. 7 over 16 out there. X to the 8 dx. And now from here we do n plus 1 over n plus 1, so 7 over 16 times 1 over n plus 1. And it's going to be 8, so 1 over 8 plus 1 times x to the 8 plus 1. So that's going to be 7 over 16 times 9, or 1 over 9, times x to the 9. So 16 times 9, don't know that off the top of my head. I think it's probably 144. Yeah, because 6 times 9 is 54, and 9 times 10 is 90, so 144. So 7 over 144, x to the 9. And again, if we were to do the derivative of this, we bring that 9 out, we multiply, we divide 144 by 9, since we're trying to cancel out that 9. 144 divided by 9 is going to be 16, so 7 over 16 times x to the 9 minus 1, which is going to be x to the 8, which is what we started with. And you can keep on doing practice of that, but let's get into some more weird, or not really weird, but some more important ideas. And that's integral of e to the power of x is going to be e to the power of x dx. I should put dx for all of these. Integral of 1 to the power of x, 1 over x dx is going to be ln absolute value of x, because we actually don't know, well, this is all plus c, of course, but we don't know why ln, so x can't be negative. The reason we have absolute value signs for ln x is because if you do the derivative of ln to the negative x, like negative x is not equal to x, so we have to do chain rule, which again is going to be f prime g of x times g prime x. So g prime x, in this case, derivative of negative x is negative 1, so we're going to have negative 1. This is going to be 1 over negative x. Derivative of ln is 1 over something, so 1 over x. That's going to be f prime of g of x times negative 1, which is g prime of x. Negatives cancel out, and you still get 1 over x. So the derivative of ln x is the same as the derivative of ln of negative x. So to account for that, we need to include the absolute value symbols because ln of x and ln of negative x both have the same derivative. And then what are some other important ones? You need to know your trig ones relatively well. So integral of sine x dx is going to be negative cosine x plus c. Again, that's just because cosine differentiates to negative sine, so we want those negatives to cancel out, so we have to have a negative out there. So we get negative cosine x plus c, and by that same logic, the integral of, not sine, of cosine x dx is equal to sine x dx. And now I'm actually going to do the interval of tan x, and this one's going to be a slightly more difficult one because we're going to have to undo chain rule. So chain rule is, like we touched on before, it is f prime g of x times g prime x, right? F prime g of x times g prime x. And when we're doing this is equal to the derivative of f of g of x. When we are doing this integral, if we're trying to undifferentiate this, we have to account for this g prime x and for the antiderivative of f prime g of x. So let's do something called u sub. So we have tan x dx is what we are trying to integrate. And based on our knowledge of trig identities, we know that tan x is equal to sine x over cosine x, right? Sine x over cosine x. And now we have to split this function into a derivative of an outside function and the derivative of an inside function. So we pick a function, u, or u is just a placeholder for an existing function. So let's say that u is going to be cosine x, and then you do the derivative of u, which is going to be, well, it's not the derivative just of u, it's going to be the derivative of u with respect to x, because again, we don't actually know, well, we know that u is a function of x because we define it up here, but u is also a function of u. So we have to differentiate u with respect to x. We get du dx is equal to negative sine x based on our knowledge of derivatives. And then if du dx is equal to negative sine x, this is a matter of preference. I like kind of looking at it as a substitution. If du dx is equal to negative sine x, when we plug in, well, we can try and solve for dx so that we can just plug that into here. So when we multiply dx to that side and then divide by negative sine x on both sides, or simply swap those two, we're just going to get dx is equal to negative du over sine x. And now, since we know what dx is, we can just plug it in for there. So let's write that out. This is sine x cosine x times negative du over negative du over sine x. And let's write u for cosine x because we did define cosine x as u. And this was equal to d of x, right? So from here, we simply cancel out these sine x's. Oops. We cancel out those sine x's and we're left with the integral of negative du of u. Now we take out that negative, and we have the integral of 1 over u with respect to u, and that's just going to be ln absolute value of u being cosine x, so we have negative ln of cosine x plus c. So what did u sub do in that situation? I kind of just said what we were doing. I didn't really explain what u sub is doing, but u sub is when you come up with some arbitrary function. We acknowledge that the integral is supposed to be the antiderivative of some derivative, so we have to assume that if we see a function inside of a function, there is chain rule happening, right? So we have to find g prime x, and we have to find f prime g of x. And so in order to do that, we have to set the smaller function, or it doesn't have to be the smaller function, it can be any function. We have to set that function equal to like what would be considered the inside function. In this case is going to be cosine x, and then we find the derivative of u with respect to x, and then we solve for dx so that we can plug in a du, and then we integrate with respect to u, and that whole thing was just to simplify our problem. Instead of having a function inside of a function, or what is essentially the already completed derivative of a function inside of a function, we have just one function, and that is a function of u. U is a function of another function, right? In our case, u was a function of cosine x, so when we differentiate with respect to u, we have to differentiate u with respect to x. I'm making this a lot more complicated than it is, I promise. All that u sub is doing is undoing chain rule. We simply set we set the inside function to u, then we differentiate with respect to x, we solve for dx, we plug du back in, and then we integrate with respect to u. That's what u sub's doing. It is simply undoing chain rule, and it's not possible to undo quotient rule. At least not yet. We need to do integration by parts. I am somewhat skipping through this because I will do a rather long practice video of integrals in the near future. Integrals are obviously very important, and I'm not going to be doing actual practice too much today. I just want to have all of the important ideas on paper, and then once we get into an actual example video, I'll have a opportunity to expand on these ideas a little bit more and to show how to apply these ideas in a more concrete fashion. So yeah, this video probably isn't the greatest if you just want to know how to do integrals, but I hope it's helping in learning what the integral is and what it's used for. So from here, let's talk about integration by parts. So in order to do integration by parts, which in case I haven't said it, it's just a way to undo product rule. The way to do that is to just kind of prove how it works. Let's do product rule out right now. We know that u v prime, well, probably I should use f of x, g of x notation, then we'll use u v notation in a little bit, but f of x, g of x is a product of two functions. So when we do ddx of this, we will get f prime times g plus f times g prime. This is product rule. We proved this a while ago, but now we have to integrate both sides, right? So let's integrate both sides with respect to x. Since derivative and integration are, inverse operations, we can simply cancel that out, and we're left with f of x, g of x. is equal to the integral of f prime x g of x plus f of x g prime x dx. Well, that integral, I'll put dx over there as well, because we can split these integrals. That's one of the properties that we were talking about. And now we will solve for f of x g prime x so that we can actually have a formula that we can use for integration by parts. And then when we solve for this, we have to subtract this from that side. So we're left with the integral of f of x g prime x dx is equal to f of x g of x minus f prime x g of x dx. Now, you won't always be able to use, well, you will almost always be able to use integration by parts for most functions that have product rule, but it won't always be perfect. It'll be, it'll oscillate, it'll do some somewhat strange stuff, which we will talk about in that example video. But for right now, let's say that u, just for the sake of brevity, let's say that u is equal to f of x and g of x is equal to v. We can describe all of this. F of x is going to be u, g prime x is going to be v. So we're going to be left with the integral of u dv. So the integral of u with respect to v is equal to uv minus the integral of v du. That's just, a way of writing what we have right here. So du is going to be f prime x dx, right? We're just differentiating this function of u with respect to x. And then derivative of v is going to be g prime x dx. Because again, even though v is defined as a function of x, we do have to have the derivative of v with respect to x, then we multiply dx to the other side. And so that's why du is used for f prime x dx, and dv is used for g prime x dx. And yeah, so we will do some examples of how this works, but just a quick introduction to the type of thinking that we'll need to use for integration by parts. Let's do the integral of ln x dx. So we have to find a u and we have to find a v. U is almost always going to be easy to differentiate, while v has to be easy to integrate. That's why the reason we want this to be easy to integrate, or v to be easy to integrate, is so that when we do v du, du will be nice and simple because u is supposed to be easy to differentiate, and v will be nice and easy to integrate because we don't have to do too many operations to get the ball rolling for the actual integration piece. So u in this case is going to be ln x. We know that derivative like the back of our hand. We know that this is going to be du is equal to 1 over x dx, right? And then dv is supposed to be what's left. So ln x is u, which means that dv is going to be 1 dx. And now let's integrate 1. So we're going to have 1 over 1 plus 1 times x to the 1. So because, x to the power of 0 is what 1 is, so this is going to be 0 plus 1, which is going to be 1 over 1 plus... Wait, what? I don't know. It's not 1 over 1 plus 1. It's supposed to be... let me write this out correctly. So 1 is equal to x to the power of 0, right? So if n is equal to 0, this is going to be 1 over n plus 1, so 1 over 0 plus 1 times x to the 0 plus 1. So this is going to be 1 over 0 plus 1, which is 1, times x to the 0 plus 1, which is 1, so x. which means that the integral of dv is supposed to be x. Again, this doesn't matter too much right now. We will talk about how to integrate these functions a lot easier, and we will do quite a bit of practice of both indefinite and definite integrals just to really get a grasp of the subject. But v is equal to x, and now we simply plug in uv. So uv in this case is going to be x times times ln x minus the integral of v du. So x times du, which is 1 over x, dx. Now those x's cancel out, then we are left with x ln x minus the integral of 1 dx, which we said was x, so we're left with x ln x minus x plus c. Alright, from there, we don't have anything else to do. That will be the integral of ln x dx. And yeah, I mean, this wasn't a super in-depth video. I hope that you saw some properties that were important, and you have a very, very brief, rather poor introduction to how to use usub and how to use integration by parts. But we will, do a bunch of practice. Do not worry. We're going to do way too much practice in a little bit. But yeah, that's integration, or at least, a very basic introduction to the ideas behind integration. And now I do want to talk just a little bit about multiple integrals. So you can kind of skip this part. This is more just for the sake of interest, but multiple integrals, or double integrals, triple integrals, there is obviously many different types of multiple integrals. That is when you have multivariate calculus. So you have several different variables. You might be thinking that we are working with different variables. We have y, we have x, but y is a function of x. When you integrate y, you're actually just integrating with respect to x. On a Cartesian plane, or on a coordinate plane where y is not a function of x, and we have to do a function with two variables, f, x, y, we have to do a multiple integral. And this is what I kind of want you to leave with. If f of xy is equal to, some value, we are going to do, we're not going to do anything because, this isn't multivariate calculus just yet. When we are doing some, definite integral, we're going to do two integrals. We're going to have to do with respect to dx and then with respect to dy. And I always find this interesting because what's happening is you have a curve, right? fxy is some type of a curve, but instead of just being, area under the curve of some 2D plane, you're actually doing something in 3D. You have depth. You have depth as what you're calculating. So you have to do a double integral, one with respect to your x values, or width, and then the rest in, if this is y, this has to be z, so that is not y over there. But you are integrating with respect to y as well, because you're seeing the change across this interval of z values, or depth. So when you're doing multiple integrals, which I think we might actually do a practice problem in multiple integrals in that video, we're just going to be seeing the volume under a curve. Not under a curve, under some type of region. I know I'm not making too much sense right now. I kind of don't want to get into all of it. We have been doing univariate calculus for a while, so I don't want to be too confusing, but just to give you something to think about, if we have more than one value, not more than one value, more than one variable that f is impacted by, and we have an xyz plane instead of an xy plane, we can actually see volume instead of area, right? Because volume is just area with a different, well, with an extra step. So we can even look at the volume of a prism. So area is equal to base times height, and then volume is supposed to be area of the base times like length or width. It doesn't matter too much. We'll use width. Uh, but yeah, this is volume is simply area with another dimension. So if this is the area of a rectangle, you give another dimension z, or like width, you give more dimension, and instead of just finding the area of the base, you're finding the volume of the entire region, which is very interesting. And in that example video, we're not going to go too much further than giving a constant value, because while I do want to challenge you, I do want to also keep us within the realm of univariate calculus when we are learning univariate calculus. So, yeah, that was a very, very poor explanation of integration. I thought the first half of the video was okay, but yeah, that second half of the video, maybe I'm just tired, but I feel like that wasn't super accurate. I did kind of rush through that definition of integration by parts and by u sub, but we will do a ridiculous amount of practice. So, you know, don't worry in case you watch that video. I feel like by the end of it, you will be a lot better at integration by parts, integration by u sub, integration in general, definite integrals, because we are doing a lot of examples. And we're going to do, one or two multiple integrals with constant f of x, y's. So, yeah, we're not going to do f of x, y, z or anything, but we will just kind of talk about that. And yeah, if you enjoy this video, please comment down below. If you did not enjoy this video, constructive criticism is always encouraged. And if you're not in the mood for a comment or constructive criticism, then you can just kind of, I don't know. It's been a while since I've worked out, actually. I'm trying to think what I last did. You can do some diamond push-ups. Might have already said that one. You can do some diamond push-ups. And for my album recommendation of the day, what album have I been listening to a lot recently? Been listening to that Audrey Nuna record. What was it? I think it was called, oh, yes, A Liquid Breakfast. And, like, I wouldn't say it's like a masterpiece or anything. No offense. I thought it was very good, especially as like a debut effort. And it does, speak to her strength as an artist for coming out with such a cohesive debut record, but it's also imperfect. Production's not insane. Songwriting flows are very unique. I feel like if you listen to an Audrey Nuna song, you know it's Audrey Nuna. It's the intonation, it's these like strange, unexpected metaphors and similes and like bars, like bar work that's honestly just weird, in like a good way. Like, it kind of makes sense. It's like, it's the same thing as like MF Doom, Because you sort of kind of know what he's talking about, but you also have no idea what he's talking about. And Audrey's the same way. A lot of her songs are, at least to me, maybe I'm just not, you know, well versed in enough slang, but I swear to God, most of the things that she says just make no sense, but it sounds good. And there are a lot of just, you know, pretty good songs in this album, especially for a debut, which is impressive. And, like, obviously she still has a lot of room to grow, and this isn't like a perfect debut or anything. There's definitely room for improvement, but I do encourage you to listen to a couple of the songs on this like album, and even if you do listen to it all the way through and still don't think that it's great or anything, I still believe that she has many many years ahead of her where she can develop as an artist and keep growing and changing her sound and making it more I wouldn't say unique. I think an Audrey Nuna song when you listen to one. But yeah, she can make it more refined. And that's all I really want from her. I think that this is a very good start to like a career. I mean, she's obviously been doing music for a while beforehand, but this is obviously a good starter point, and it does include quite a few of her most popular singles. But yeah, it's just a good. I wouldn't say amazing. Like this is probably the best definition of a 7 out of 10 for me. It's a good album, and I encourage you to listen to it. It's definitely unique. Uh, like I I again like maybe the production is relatively. I wouldn't say bland or anything, but it's not breaking any barriers. But the writing that Audrey has is just so it's so Audrey, It's very her, and you can kind of tell that by the end of the album. You know that she's an artist to look forward to. So yeah, that's pretty much it. Uh I I know I mixed up the this video's just been kind of a mess. I'm not sure if I'm even gonna upload it at this point. It's not a great video. But yeah. Uh bye.